Hi, I am Adam Tilted. Welcome to Orbit at a Tilt. Today we are going to talk about neutron stars. Just a moment, I'm having a little technical difficulty here. All right, you ready? Let's go. Neutron stars are some of the most bizarre objects in the universe. So we're going to talk about what they are, where they came from, and some of the flavors that they come in. But first I want to take a look at the night sky this week. Couple things happening. Jupiter has been in retrograde, which means that it looks like it's going backwards in the sky in relation to the sun. But on Wednesday, it'll look to us like it stops, and then after that, it'll go the other direction. So let's take a look at this in the simulation. So Jupiter is here, and it's next to the star Zubinagaloobi. I know. Zubinagaloobi is the name of this star right here. Okay, so I'm going to, if you want to see how that's spelled, Zubinagaloobi. It is a little more than 75 light years away from us. Excuse me. So Jupiter is over here. Now we're going to advance the days, but keep the time the same, and we're going to see how Jupiter's position in the sky changes. This is back in May. So you'll notice as we get closer to June, Jupiter is getting closer to Zubinagaloobi. It eventually passes it. And see, it's going from east to west, which is backwards from how the other planets are going. So that's why it's called retrograde. Now, once we get over to closer to today, let me move this out of the way, then you'll see it's going back the other direction. It's going past Zubinagaloobi again. Zubinagaloobi. Man, they're making it hard for me today. Zubinagaloobi, and you can see it's pretty close. So if you were watching over a period of time, you would see Jupiter stop and change direction. This is a really fun activity to do. If you have a backyard telescope, I apologize. My eyes are going crazy because of allergies today, so sorry for the puffiness and redness. But if you have a backyard telescope, or if you have the equipment to take some photographs from night to night and see how the position changes, even if you just notice with your eyes, just go out and look. Jupiter is high in the sky right now all night long, so it's very easy to view. Just pay attention to where it is relative to the other stars and stuff in the sky, and you'll notice things like it's in retrograde. All right. Now, new moon is on Thursday, and then on Friday, the moon is at perigee. So this is a good opportunity to practice some vocabulary. So I don't know if you remember, last week, Earth was at aphelion, and that was when we were furthest away from the sun in our orbit. The opposite of that is perihelion. That's closest to the sun. So, ap means away. Peri means close. So aphelion means close to the, far from the sun. Away, away. Perihelion means closest to the sun. So the same thing, we use the same prefixes for the moon and the earth. So when the moon is furthest from the Earth in its orbit, it is at apogee. And when it is closest, like it will be on Friday, the 13th, it will be at perigee, which is in the part of its orbit where it's closest to the Earth. Now, this does not have anything to do with the phases of the moon. The phases of the moon are caused by the position of the moon and the sun and the Earth. So that they're not related, but it does happen that on Thursday is the new moon. So on Friday the 13th, it's going to look like there's no moon. There's going to be just a little tiny sliver, but you might not be able to see it. But by Saturday, let me get rid of all of this stuff up here. By Saturday, we've got the Mercury. Oh, wait, sorry. We'll move ahead to Saturday, the 14th. And if you look over here, the waxing crescent moon, it'll be just a little crescent, will be 2 degrees north of Mercury. And 2 degrees is about the width of your finger at arm's length. So just after sunset, if you can see the moon, then take a look for Mercury. Mercury is typically difficult to see, but with the moon as a marker, it'll be a lot easier. All right, so let's talk about neutron stars because they're crazy. A couple weeks ago, excuse me, maybe last week, I talked about black holes, right? And black holes form when a star that is much more massive than our sun reaches the end of its life, explodes, and collapses in on itself. Neutron stars are not as big. They didn't start off as big as stars that create black holes, but they are bigger than our sun. So when those stars run to the end of their life, remember a star has a nuclear explosion going on in the middle, and that is providing an outward force. Gravity is pushing in, creating that inward force, and that as long as that's balanced, the star is stable. That explosion is being caused by nuclear fusion. So hydrogen atoms, which are basically a proton and an electron, are being fused together to make a new atom that has 2 protons and 2 electrons. That's helium. That process goes on and on and on, making helium fuses to make carbon, carbon fuses to make neon, neon fuses to make oxygen, which fuses to make silicone, which fuses to make iron, and then we have a problem. Because iron cannot fuse to make a new element. So the star has run out of fuel. So the force of that explosion that is balancing against the gravity fades out. Gravity takes over, the star collapses, the outer layer of the star gets blasted out into space, and then the core of the star shrinks down into a tiny, incredibly dense object. So, and it's so dense that the electrons and the neutrons get forced to occupy the same space. The protons and electrons get smushed together to form a neutron. And then those neutrons just are like this soup of dense neutrons. So dense that It's probably 3 times the mass of our sun, but it's about the size, the radius of Manhattan. So it's incredibly dense. Those pressures, because of angular momentum, cause it to spin incredibly fast, hundreds of times a second. And that spinning creates, makes it bulge out in the middle and emit radio waves. And those radio waves, as the star is going around, it's kind of like a lighthouse swinging those radio waves around. And we can detect those, and we call those pulsars because they are amazingly regular. And so we can use them to keep time. We can also use them to measure distance. They're very useful. Some neutron stars get even crazier. Well, by the way, there's about 2,000 pulsars that we know about in the Milky Way and the Magellanic Clouds. Those are 2 satellite galaxies. They're really, what do they call them? They're not, I forget, irregular. They're irregular galaxies, so they're not like whirlpools or anything like that. But they're close by, so we can observe them pretty well. But there's about 2,000 of these pulsars that we have observed. And about 1 in 10 neutron stars does something that we don't understand. During that spin-up process, something happens that generates a unbelievably huge magnetic field. Now, you probably are not familiar with how magnetic fields are measured. I'm not really. But I know that the Earth generates a magnetic field of about 25 Gauss. Gauss is the unit they use for measurement. A magnetar generates a magnetic field of 1,000,000,000,000 Gauss. Now this is so strong it actually bends the atoms. It bends them as they enter. It's amazing. We don't know exactly what's happening there, what causes it, but incredibly violent. And those neutrons on the outside form a hard crust because they're not as energetic as an active star would be. So they cool enough to form a crust around it, a hard crust. And remember, it's spinning, so it's like a squished ball. And if it starts to spin faster, which it can do for a lot of reasons, one is if there's a nearby star that it's pulling material from, then that changes the shape and it creates a starquake. Just like an earthquake on Earth is caused by the motion of the tectonic plates, a starquake is on the surface of a neutron star, particularly magnetars, and it cracks. Now we've measured some of these cracks, these starquakes. The largest one that we've ever measured lasted about 1/10 of a second, and it released as much energy as our sun would release in 100,000 years. 100,000 years worth of sun. That is crazy. Now, obviously, we haven't been able to study these up close. So a lot of what I've just told you is based on calculations, comparing it to things we do know, and making predictions that are still waiting to be proven true or untrue. Because they're very mysterious. But they're also very dangerous. The radiation that's coming from these things, would make it very difficult. Even if we could get to one, it would make it difficult to survive long enough to study it. Okay, so that is the basics of neutron stars. In a nutshell, they are stars they're remnants of supernova explosions of stars that are bigger than our sun, but not big enough to collapse into a black hole. Oh, and by the way, since we've been talking about pulsars and magnetars, you might have heard of quasars, and you might be wondering, are those in the same family? And kind of, but not really. Quasars are a phenomenon that occur around supermassive black holes. So they're more related to black holes. If you're interested in quasars, let me know. We'll talk about what those are. Okay, so that's it for this week. Take advantage of the summer nights if you have good weather. Go out and look at the stars. There's a planet parade going on all night. You can actually see every planet that you can see with the naked eye is up during the night. So I encourage you to go out and look. Even Uranus, you can pick out with some binoculars if you have a decent set of binoculars and you know where to look. And Neptune, if you have a telescope and you know where to look, you'll be able to see that as well. So happy star watching, and until I see you again, keep looking up. Bye.